Hello students, today we will explore chapter 9 Hydrocarbons. This is our theory part 17 and we will cover NCERT section 9.5.6 in it. This is our disclaimer. Now, after attending this lecture, you will be able to understand the directive influence of substituents in monosubstituted benzene. So what is monosubstituted benzene? In which one hydrogen of the benzene is replaced by a different functional group. Now, this replacement have impact on its reactivity and as well as physical properties. So, today we will explore that angle where we will see the difference in reactivity of your substituted benzene, the monosubstituted benzene, depending on the substitution that it has undergone. If I talk about the specific name of the NCERT section that we are going to cover, so we will be covering 9.5.6 directive influence of a functional group in monosubstituted benzene. After that, we will summarize the whole thing with a short summary. Let us start by introducing the concept of electrophilic substitution in aromatic compound. This is a key reaction type where an atom, usually hydrogen on a benzene ring, is replaced by an incoming group called an electrophile. We will see how the position of substituent is influenced by the group already attached to the ring. So, looking at what happens when we have a monosubstituted benzene, meaning benzene with one group already attached to it. When it undergoes electrophilic substitution, we can get three different type of disubstituted products. These are ortho, meta and para derivatives, depending on where the new group is getting attached relative to the existing one. So, these ortho, meta and para products are not formed in equal amounts. The ratios depend on the nature of the group already present on the ring. This means some positions are favored over other and we will explore why that happens. The image illustrates electrophilic aromatic substitution on a benzene ring where a substituent X is already present. An incoming electrophile E+ can attack three distinct positions relative to X. Ortho, the electrophile attaches to the carbon atom adjacent to X, 1,2 disubstituted as we can say. Meta, the electrophile attaches to the carbon atom separated by one carbon from X, 1,3 disubstituted. Para, the electrophile attaches to the carbon directly opposite to the X, which is 1,4 disubstituted. Now, let's talk about what controls where the new group attaches. This is called the directive influence. The group already on the ring has a big effect on the position of the next substituent, and this is a fundamental idea in aromatic chemistry. The key point is that the position of substitution depends entirely on the group which is already present. For example, some groups pushes electron towards the ring and where other pull electron away, and this changes where the new group will go. Importantly, the nature of the incoming group or the electrophile does not decide the position. It is the group that is already present on the ring which decides the main influence. This is a common point of confusion, so make sure to remember the distinction. To sum up, the existing group on the benzene ring determine the product through its electronic effect. These electronic effects can either be activating or deactivating certain positions on the ring, guiding where the new group will attach. Let's look at the factor that affects the directive influence in hydrocarbon. Directive influence refers to how a substituent on a benzene ring can control where new group attach during a chemical reaction. Understanding these factors help us predict the outcome of substitution reaction. Now notice that the directive behavior of a substituent is determined by a combination of two main electronic effects. These effects are responsible for how electrons are distributed in the molecule, which in turn affects where new atom or group will attach. Let us break down what these two factors are. The first effect is called the inductive effect. This happens when atom or groups pull or push electron through the sigma bond in a molecule, usually due to electronegativity difference between the two atoms or groups. For example, If a chlorine atom is attached to a benzene ring, it will pull electron towards itself, changing the electron density at different positions on the ring. The second effect is the resonance effect. This involves the movement of electrons through the pi system of the benzene ring, allowing electron to be shared or delocalized over several atoms. Both the inductive effect and resonance effect work together hand in hand to determine the final directive influence of a substituent. Now, continuing by looking at the factors that affect the directive influence in aromatic compound. First is inductive effect. Arises from the electronegativity difference between the substituent and benzene ring, we know it. Now let's focus on electron withdrawing groups with reference to the inductive effect. These groups have atoms that are more electronegative than carbon, so they pull electron density away from the benzene ring through sigma bond. This makes the ring less reactive or deactivates it, especially towards reactions like electrophilic substitution. For example, fluorine, chlorine written as F and Cl are classic electron withdrawing group because they pull electron away. They make the benzene ring less likely to react at certain position. Remember, the more electronegative the substituent, the stronger is their deactivating effect. Coming on to the electron donating groups, so they show a positive inductive effect or plus I effect. Alkyl groups like methyl or ethyl push electrons towards the benzene ring through sigma bonds. This slightly increases the electron density into the ring, making it a bit more reactive or weakly activating it for further reactions. For example, we can have a CH3 group or a C2H5 group as an electron donating group. They make the benzene more likely to react at certain position with respect to the incoming electrophile, but their effect is weaker compared to other activating groups. Now, what are those factors that derive this other activating group? So that factor is the resonance effect, also called as the mesomeric effect. Resonance involves the delocalization or spreading out of the pi electrons between a substituent and the benzene ring in case of your electrophilic aromatic substitution. This effect is often stronger than the inductive effect, and it plays a big role in determining where new group will attach onto the ring. First, let us consider electron donating group, which are called plus R groups. These groups push pi electrons into the ring, increasing the electron density. This makes the certain position on the ring like ortho, para more reactive to the incoming group. Examples, so the hydroxyl group written as OH, so they donate electron into the benzene ring. This increase the density on the benzene ring. Now, it makes the ortho and para position especially more reactive. We will see about it in detail. And so now notice how adding an OH group can change the chemical behavior of the ring. On the other hand, we have electron withdrawing group called minus R groups. These groups pull pi electrons away from the ring, reducing the electron density. This makes the ortho para position less reactive to the new groups. Example, the NO2, which is an electron withdrawing group, these decreases the electron density at the ortho and para position, making these sites less likely to react. So if you are considering your methyl group, which shows a plus I effect, and the OH group, which shows a plus R effect, so OH will be more ring activating as compared to the methyl group, because your OH is donating electrons through resonance effect, which is more powerful in comparison to the electron donating effect of your methyl group. But this is not the case always. There can be cases when your inductive effect is more predominant than your resonance effect. We will talk about them. Now let us start by looking at how the nature of the product in the hydrocarbon reactions depend on the substituent already present on the molecule. This sets the stage for understanding why different products can be formed when we introduce a new group to the hydrocarbon ring. So based on the nature of existing group, two sets of products are possible. What are those? The first is ortho or para directing group. Okay, so one of the product is major, so it can be a ortho product or it can be a para product. So this is the first set. The second set is meta-directing group. Okay, in ortho and para, both are produced, but one is the major, one is the minor. Okay, so this is the first set. In the second case, only meta are produced in predominant amount. If I try to represent the same thing visually, you can see here that we have a substituent on your benzene ring as X. Now it is directing the incoming electrophile E+. Now depending on the nature of X, the electrophile will preferentially attack the ortho, para or meta position. Activating groups like OH, NH2 are typically ortho para directors, enhancing electron density at these positions. Deactivating groups, example NO2 or the COOH, are generally meta directors, withdrawing electron density and making meta positions relatively more reactive for electrophilic attack. The diagram shows the formation of ortho, para and meta products. Let us start by looking at the ortho and para directing groups first. These are important concepts when we study how different groups affect the position where new atoms or group are attached to a benzene ring via reaction. We will see how these groups influence chemical reactions and why their position matters. Now, let us define that what are ortho para directing groups. These are groups attached to a benzene ring that guide a new group onto the second position or to the fourth position. So you can say them as ortho para directing groups. So your ortho position is adjacent to the position of your existing group and your para position is opposite to the position of your existing group. This direction is crucial for predicting the outcome of your substitution reaction. The image illustrates the electrophilic aromatic substitution on a benzene ring substituted with the group G, which is an ortho para director group. This means that when an electrophile attacks the ring, it preferentially directs the incoming group to the ortho, which is the adjacent position, and para, which is the opposite position relative to the G. The reaction shown as involving EA results in the formation of an ortho product where E is the ortho position and a para product where E is at the para position. The byproduct HA is also formed. Ortho para directors are typically electron donating groups that activate the ring towards the electrophilic attack at these specific positions in most of the cases. Now your ortho para directing group have some deviation from the activating part. So they can be also of two types. So there can be cases that it can be activating group or it can be a deactivating group. So we will talk about those. So there is only one example where your ortho para directors are deactivating. So continuing looking at the ortho and para directing groups. So first let us talk about the activating groups. These are groups that make the benzene ring more reactive, especially at the ortho para positions. These groups play a key role in determining the outcome of the substitution reaction. Activating groups are usually electron donating or EDGs, so they are abbreviated EDGs. This means they push electrons into the benzene ring, increasing the electron density at the ortho and para position. This higher electron density makes these spots more attractive for incoming atoms or groups during a reaction. The main reason that these groups activate the ring is because of something called the positive resonance effect, often written as plus R effect. This effect allows the group to share its electron with the ring throughout resonance, making certain positions highly electron rich and more reactive. Examples are NH2, NHR, OH, OCH3, NHCOCH3, OCH3, CH3, C2H5. Each of these groups donates electron to the ring in slightly different ways, but they all make the ortho and para position most likely to react. Now the image illustrates the aromatic ring substitution in a benzene ring substituted with group A, which is ortho para director. So we have already seen this, but here G is your activating group rather than a deactivating one, and it is directing your incoming electrophile E onto the ortho and para position, creating ortho product and your para product. Apart from this, we are also getting HA. Now continuing further, what are the examples of activating group? So we talked about some examples. So we have seen OH, NH2, then we have NHCO, Cr. So we will look at each of them. I would say some of them. with the help of their resonance structures. For that, we are taking the phenol group, so that one would be enough to explain how all other remaining groups can be acting as a electron donating group and creating ortho-para isomers of the product. Got it? Now, if you look here, then this is the resonance structure for the phenol. Here, the structure are named as 1, 2, 3, 4 and 5, where the structure number 2, the structure number 3 and your structure number 4, they clearly depict that the lone pair are being pushed onto the position ortho and para, making these 3 positions. Okay, so the 2 ortho positions are same. So it is, since the molecule is symmetric, you can either substitute on the right, on the left, you will get the same product. So basically on the 3 position it is activating the carbon by increasing the electron density, and 2 of them are identical. So you can clearly say that 2 possible positions are there where your incoming electrophile can attack, because electrophile are electron deficient and the electron density is increased on the ortho and para position. Further, we can conclude that these resonance structure have negative charge at ortho and para position of the ring. Ortho position are directly next to the OH group and para position is opposite to that. This means that these positions have extra electron, making them more reactive to the positively charged species or electron deficient species like your electrophile. Next, because of this high electron density at the ortho and para position, these spots are especially good for attracting electrophiles which are positively charged or electron seeking species. So activating groups like OH directs new substituents to the ortho and para position on the ring. This is a key in understanding how ring reactions happen on aromatic rings. Now continuing further, next we will talk about the deactivating groups, means the ortho-para directing groups which are deactivating at the same time. So these are exceptions, I would say, because they are not more examples of being ortho-para directing and deactivating at the same time. We will look at that. So halogens are a special kind of deactivating group which are ortho-para directing as well. So halogens are moderately deactivating group. This means they don't stop reactions completely, or they don't make the ortho-para direction or the ring completely negligible for the electrophilic aromatic substitution, but they do make the ring less reactive compared to the simple benzene ring. Keep in mind that all deactivating group acts the same way. Now, why it is happening? So the predominant factor for the halogen to be acting as a deactivating group rather than the ortho-para directing group is that they have a very strong minus I effect, which is due to their high electronegativity that pulls the electron from the benzene ring. So basically it includes the fluorine, chlorine and the bromine. So if you see fluorine, chlorine or bromine attached to the benzene ring, you know that this will influence where new group can attach and how fast the reaction goes. Halogens atoms are a special case of a ortho-para directing group. So you can just sum it up and say this. Now moving on further, we will see how it is happening and why they are ortho-para directing instead of being the electron withdrawing group or the ring deactivating group. Now let us look at the example of deactivating group. Deactivating group makes the benzene less reactive. We have seen this towards the incoming atoms or molecule due to the higher electronegativity of the halogens. Chlorine is a classic example and we will see how it affects the ring. Considers the resonance structure of benzene, chlorobenzene. So resonance means the electron in the molecule can be shown in different arrangement which affects how the molecule reacts. So here is an image. It illustrates that chlorine is increasing the electron density on 2, 3rd and 4th position. Got it? But basically this is the only case where your resonance effect is dominated by your inductive effect due to higher electronegativity of halogen. As a result of this, the electron density which is donated by the halogen is overshadowed by the electron pull through the sigma bond. Got it? So basically, chlorine's electronegativity causes it to withdraw electron density through the sigma bond, and it is dominating the pi donation through the resonance effect. So this strong inductive effect makes the entire benzene ring less reactive towards the electrophiles. Chlorine also donates a pair of electron in the ring via resonance effect. We have seen the structure, and this resonance specifically increases electron density at ortho and para positions. Therefore, in conclusion, we can say that despite chlorine's stronger deactivating inductive effect slowing the reaction, it is weaker, and resonance effect will guide the incoming electrophile to the ortho and para position. Now, we will shift our focus onto the meta-directing group. Groups which direct the incoming group to the meta position are called the meta-directing group. Notice how the term direct means that they control the position of the new group during the reaction. Examples are NO2, CN, CHO, COR. Then we have COOH and COOR. Notice here that each of these given elements which are attached to the benzene ring of the group, they are having a lower hybridization. I would say that they are having a hybridization in which they have a greater S character. Means if you look on to the C, it is having a sp hybridization, CHO sp2, again COR sp2, COOH sp2, and COOR sp2. So all of them are having a sp2 hybridization, which is a nature that affects their electron donating or taking tendency. Now, as I said, the meta-directing groups will influence your incoming electrophile to go on to the meta position and hence creating a meta product. Apart from this, the electrophile will be attached to the meta, so that is the thing. And apart from this, you are also getting a byproduct which is denoted here by HA. Now, moving on further. Next, we will look on a specific example to understand this thing. So, we are taking the example by looking at the resonating structure of nitrobenzene. So, we know that resonance means that the electrons are delocalized or spread out across different positions in the molecule. These delocalizations changes the electron density at various positions on the ring, which is key to understand its reactivity. Here you can see the resonance structure of nitrobenzene in the diagram. Notice how the electron move around the ring and how charges appear at different positions. Pay attention to where the positive charges are located, and this will affect where reactions are more likely to happen. The resonance effect, often called the minus R effect, is especially strong at the ortho and para position on the benzene ring. This means that these positions are more affected by the electron withdrawing nature of the nitro group. Let us see what this does to the electron density at these spots. Because of this resonance, a positive charge develops on the ortho and para position. This makes this position electron deficient or less rich in electrons. As a result, they are less attractive to the incoming electrophile, which are the species that seek out electrons. Now, the nitro group is a strong electron withdrawing group or a EWG group, which pulls electron away from the benzene ring through both inductive effect and the resonance effect. So, you know, NO2 is having 2 oxygens and 1 nitrogen, which are almost very electronegative than carbon. So, they are creating a minus I scene here, as well as they are engaging the electron towards itself by minus R effect. Inductive effects, you know, it is the way of pulling the electron through sigma bond, while the resonance effect involves delocalizing electron through pi bond. Mean the sigma electrons and the pi electrons both are being removed from the benzene. Now, both the inductive effect and resonance effect of the nitro group work together to reduce the electron density on the benzene ring. This makes the ring much less reactive towards the electrophile, which are particles that want to gain electrons. Remember. So, in conclusion, the electrophilic substitution reaction in nitrobenzene mainly happen at the meta position. This is because the meta position remains relatively electron rich compared to the ortho and para position, making it the preferred site for reaction. Now, to sum up, the meta position is favored for the substitution because it is less electron deficient than the ortho and para position. So, here we are not having a negative charge on the meta position. Instead of that, we are having a positive charge on the ortho and para. So, relatively the meta position is electron rich. Basically, this is the outcome. Now, if I ask you which is more faster, ortho para directing groups are more faster or the meta directing groups? You would clearly say that the ortho para directing groups are more faster because they are kind of increasing the electron density onto the ring. You can take this chlorine thing side apart because it is a deactivating group. Because apart from that, if you take a activating group, which is a part of ortho para director, then it will be of course showing a faster reaction as compared to the meta directing groups. Now we will just sum up our lecture with a short summary. So we started with the directive influence in benzene, where new atoms or group will attach during a chemical reaction, and this is decided by the already existing group on the benzene ring. So we can say that the substituents or group that are already attached to the benzene ring control where the new group will attach during a reaction called as electrophilic aromatic substitution. This means that existing group can guide the incoming group, and there is no means there is almost zero role for the incoming group. Yes, there is a factor which for deciding the ortho and para substitution, and that depends upon the incoming group, but it will be discussed later on. Primarily, the ortho-para directing and the meta directing is being controlled by the existing substituent and not by the incoming electrophile. Next, the results are ortho, meta and para. So these are the three positions which are possible. Ortho, which is next position or adjacent position where the existing group is attached. Then we have the para position, which is having one carbon between the existing group and the new group. Then we have the meta position, which has the one carbon between the existing group and the new group. Then we have the para position, which is just opposite to the existing group. Now, the outcome of the product, means the outcome of the reaction, is decided by the electronic effects. So they can be inductive, they can be hyperconjugation, and they can be your resonance effect. Here we have discussed more about the resonance effect and the inductive effect. Okay, so if I talk about the electronic effects, what we have the inductive effect, which based on the electronegativity, and here the electrons are pulled by the more electronegative element through the sigma bonds. Further, we have the plus R or minus R, which is under your resonance effect, and they pull or donate pi electron by delocalization of electron. Got it? Now, talking about the ortho-para directors, so these substituents are that direct incoming substituent onto the ortho and para position of the ring. Examples are NH2, OH, OCH3 and CH3. If you look for the ortho-para directing group and they are activating through the resonance effect, you will see a common thing in them, which is their lone pair that is donated onto the ring. But in not all the cases the lone pair can be donated. So there is a specific structure for that, and the specific structure is that your lone pair containing element should not contain a double bond. You can look here, you say about N, O or your C, all of them are containing single bond, and NO and O in the OH and OCH3 and NH2, all of them have a tendency to donate their lone pair onto the benzene ring through the plus R effect. Next are deactivating halogens. So here also the fluorine, chlorine and bromine, they have lone pair, but due to their higher electronegativity, they will pull electrons rather than pushing them. So although they are ortho-para directing, but they are ring deactivating. Then what are the positions that they direct the group onto? So they direct the group onto ortho and para, and out of them one can be dominant one. Next we talk about the meta directors. So these are groups that direct new substituent to the meta position, which is one carbon away from the original group on the benzene ring. Meta directors are always deactivating. Remember, this is very, very important. Meta directors include groups like NO2, CN and COOH. These groups strongly pull electrons away from the ring, making it less reactive and favoring substitution reaction at the meta position. They are meta directing groups, and if they are present, the new group will be attached onto the meta position. This is a reliable rule, and that helps us to predict the outcome of the many benzene reactions. Now, meta directors have both minus I and minus R effect, meaning they withdraw electrons through both sigma and pi bond. This doubles the withdrawing and makes the ring very less reactive and ensures that substitution happens at meta position only. This was all for today's class. Thank you for your attention.